Okay, friends, we were seeing 555 timer and how we can make different multi-vibrators with this device. So the device is one of the options is to make a stable multi-vibrator. So in this a stable device, the signal is increasing, decreasing, increasing, decreasing. Why? Because here the capacitor here is charged and discharged, and there is a memory effect due to this SR latch, and that memory effect is making this trigger stages in two different points. So the same way that we did this, going like up and then coming back like this was happening, right? I mean, so it was going like this, and then on the way back it was coming, and then the voltage trigger point was different. So that was one of the use, and the circuit wise, it is mentioned here that the chip, there is a chip for this. So this 555 timer chip, 555 timer chip was, having some input stages. So when you connect the threshold to trigger, and then connect that to a capacitor here, it is the way to make an astable multi-vibrator. So I mean, we had some different things we paid attention, and if you look at last year's exam questions, sometimes we use the same 555 timer. Sometimes, we replace this maybe transistor with other type of transistor. Sometimes, we did something like, and externally we put maybe active devices, transistors for the external device, just to make some variations of this concept to ask as an exam question. But this was the idea, and then we said that if you do this, the time of charge up and charge time times have different taus, and while it is discharging, tau was tau 2, and while charging it was tau 1, and tau 1 time was I think what did we mention about it? It was, yeah, RA plus RB was, tau 1 was RA plus RB times C, where tau 2 was only RB times C. So due to that different charge up time and charge down, we had different X and Y values, but still it was operating as a clock generator, for example. So one way to make this thing maybe more symmetric is to add up some elements, as I told you, and this is also some of the things that we ask in the exam questions again, like while charging, maybe it will be charged through another element here, and then while charging it goes through here, And then while this charging, maybe this was RC. And so charging could be done through here. Okay, charging. And then this charging could be through another element. So maybe I shouldn't have drawn it there. I am going to take it back here. Okay, maybe in this one. So what I mentioned in the previous one, could be applied here. So the charging path, we can say that this is the charging path. And then this is the maybe this charging path. So if you make this this way in the charging path, maybe you can make RA plus RC to be equal to RB to have 50% duty cycle. This is the way to make things, for example. So, we had different versions of this. Again, normally, you cannot play with the internal circuitry of this 555 timer, but for the exam, just to make maybe exam questions, interesting exam questions, we change maybe this block, or sometimes we change this just to see if you are you are aware of the things fully, for example. So this is the A-stable multivibrator, and it was increasing up to a certain point, like 2 VDD divided by 3, and then this charging to VDD divided by 3. Okay, so of course, if you change these resistor ratios, then this numbers will be different, right? So in the exam, sometimes we make this in 10K just to see if you will be able to find, that switching points, and then I mean, we try to make maybe interesting, circuits like that. Or we make sometimes ask, design questions like, how can you make this thing 50% duty cycle? Or, what should be the value of this RB so that, the transistor is going to be in saturation, for example, those kind of things. But those are small variations. So, A-stable multivibrator is one of the most popular usage of this 555 timer. By adjusting the R, RA, RB, and RC, you can set the this time, and then this time, 1/4 of this is going to be the frequency of signal. So if you don't want to make the duty cycle like this, there are other things that you can do. Let's just exaggerate, like, if this is the case, let's say duty cycle, okay? So still you can pass this to a counter and then make a signal, like each time that clock comes, it goes up and then down and up and down. So therefore, the maybe frequency is half right now. So right now this is maybe T2, okay, which is going to be 2 times T, but then this is 50% duty cycle. So that's another way of creating 50% duty cycle. Just use this thing and then maybe select the capacitor smaller and then, you know, then set it up this 50% duty cycle. Duty cycle clock signal can be generated this way also. Okay, so let's just, you know, limit this here. So this is coming from the 555 timer. And then this is generated later with a latch, for example, or with 1-bit counter, for example. Okay. So another famous circuit that we can generate here is monostable multivibrator. So if you remember the monostable multivibrator concept, in this concept, the system is stable in a steady state until a disturbance comes, and then after with the disturbance, the output will go to a different state, and even though the disturbance goes away, output will remain in that unstable state for a while and then go back to stable state. So that was the case. So you know, here, in order to you know, make this circuit operational, we connect here VDD. So reset, this was reset, you know, we set this thing VDD, so this becomes off. Okay, so you know, that reset signal, we don't need it for this circuit. So we turn that off. And what we can do is, instead of putting 2 resistors, remember there used to be one other resistor here. So that resistor we eliminate. We don't need to put that externally, but also the threshold in the previous one, the threshold was connected to trigger. Now we don't want to do that. Threshold is separate, trigger is separate, okay? So the trigger one is going to be the trigger input for the astable or monostable multivibrator. So the operation is going to be like this. So let's start analyzing. So here, the trigger signal is going to be initially high. So normally, actually, what we use this trigger signal, if it is high, it won't be triggered, okay? So the trigger means, you know, we put that into low state. So triggering mechanisms will start by putting this, let's say, to low. Okay, so when we do that, let's say this is t is equal to 0 time, okay, just for convenience. So here, the, or we can just say that, yeah. Before trigger, what happens, and after trigger, what happens. So before trigger, and then this trigger is going to be a certain time, let's say T trigger, and then it will go back to original state, okay? So this is the purpose here. So with this T trigger or voltage trigger, the output needs to change its state. So let me tell you, the concept first. So we need to find what is output, what is V threshold, what is S and R. But the concept wise, of course, we want the output to be maybe changing its state, or it can be going from low to high, and then it should be going back. So, and then this time should be equal to T, right? So that's the idea here, to make something. I mean, this can be going from high to low or low to high. I guess in this case, it goes from high to low. So in order to understand what was the output initially before trigger and settled value, we can start analyzing the circuit. So in order to understand where the circuit is staying, one thing is to assume that capacitor is maybe open circuit, or the capacitance is 0. So analyzing and finding the initial states is not going to be straightforward maybe, but the best way is to assume something and then see if everything is satisfying that assumption. So for this circuit, we can assume, okay, and assume that C is initially discharged, okay, and then check if this is consistent with the rest of the circuit. Okay, so if the capacitor is initially discharged, let's say this was 0 volt initially, okay, 0 volt. So if that is 0 volt, what is the case for the reset? So this is 0. If this is 0, what happens to output? Remember, let's say this is 6 volt. So this is 4 volt. So what is the output R? No response. Come on.
0.
Yes, 0. Okay. So this is 0. And the trigger initially was, remember, high. So it was 1 or VDD. Okay, VDD. So if the trigger was VDD, what is this? This is 2 volts. So what is this S? S will be also 0, right? So so what about the Q or Q bar? So if S and R is 0, it will be storing its previous value, right? So Q and Q bar will be depend on the previous case. So we are trying to find a possible case to create that. So this 0 volt happens when Q on is, or Q1, Q2 is in saturation. So in order to make this in saturation, this should be, output should be VDD, okay? So if this is the case, then VDD, then this is going to be 0. So everything then is consistent, you know, for this kind of case. S will be, or V threshold was what? 0, because it's connected to capacitor voltage. So the threshold voltage would be 0 until we have a trigger coming. Okay, meanwhile, until that trigger comes, S will be 0 until this comes to 0. So this will be 0. What about output? We said it is going to be VDD, right? So output is VDD because that's the amplifier or buffer. Just okay, it will be high. You're right. So things will be settled and then waiting here until the trigger comes. So this is a stable state. Everything is consistent, and this is okay, you know. So what happens if the trigger signal goes to low? If the trigger signal goes to low, I'm going to use a different color here. Maybe this red, okay? So trigger becomes not VDD, it becomes 0 volt, okay? So if this becomes 0, what happens to this? This goes to, set goes to VDD. Why? Because now, compared to 2 volts, 0, output is going to be high. When this goes to VDD, what happens to Q? Because it's set input. So set input makes this thing VDD. And then this becomes, VDD becomes 0 volts, right? So it goes to 0. This goes to VDD. I mean, Q goes to VDD. And this thing, and now becomes 0 volts. Okay, it used to be VDD here, goes to 0. So therefore, this transistor becomes off. Okay, so the capacitor voltage will charge up. Okay, capacitor wants to go from 0 volt to VDD. That's the goal of the capacitor. So still initially it's 0, initially 0. But then this goes from 0 to maybe larger voltage. So as soon as it reaches to 4 volts, then reset will be changing its position. So it will remain, this will go, and then after this, first 0, and then it will go to VDD. So let's just, you know, write this here. So during the trigger time, V threshold voltage, what is V threshold voltage? V threshold voltage is equal to V capacitor voltage. So V capacitor voltage is equal to V This is equal to V capacitor voltage, okay? So the threshold voltage is going to be starting to increase. And what is the goal of this thing? To go to VDD, okay? But things will start changing when the threshold reaches to this voltage. What is that voltage? 2 VDD divided by 3, or 4 volts. So this will be, then things will start changing after this point, okay? So this is the important point then, because output will be switching. So here, what happens to S? Okay, trigger. Trigger is affected from S. S is affected from trigger. So whatever the trigger is, S is 1 over of it. So S becomes high at VDD. And then as long as the trigger is here, it will go high and it will then come back to low. So this is for the triggering period. For the triggering periods, this will be happening to S. What about R? R will not change until this point, right? Because R is here and then it's waiting for this to reach the 4 volt. So the R will remain here at low. And then as soon as this goes high, then R goes high for a very short while, and then R is going to later on come back, because the things will change. What about the output? Output initially is going to be affected from this when the trigger comes, and then output will not change, even though S goes to high and then go to low. Output will be storing its value. So output, when S goes high, that means it is set. Set means Q becomes VDD, okay? And then therefore output goes to low because output is connected to Q bar. And then even though S goes to low, output will keep its value. Why? Because here output keeps its value due to that Schmidt trigger function of SR, okay? Keeps its value when S is equal to 0, R is equal to 0. So this temporary going high doesn't really, and then once it triggers and takes the output to high, and output meaning Q becomes high, but then output becomes low, and things will be going. So the device will change. The R becomes high again when this reaches to this point. So R goes high, and then why? Because R is connected to the capacitor, and after this, when this becomes 4 volts, it will start going to 0 volts. Why? Because when that reaches and reset goes high, output goes here, because now it's reset. Reset means this goes to high again. When this goes to high again, VDD, and then this becomes SAT again. So SAT means this capacitor will be discharging. Does it become SAT again right away? No. Why not? In fact, because the voltage here is, is 4 volt now. 4 volts capacitor, and then it doesn't really become SAT right away. So this will be first become forward active, and then C charges through. Okay, so the capacitor will start discharging very quickly. Okay, and then the current is going to be very quickly, discharging here. So C discharges through C discharges through Q2. Okay, so when you really look at the circuits, and we have analyzed this kind of circuits before, we have to be careful here. It doesn't go like this. The discharging occurs very fast, and then because with the V final voltage here, VC final is going to be what? What is that VC final going to be? VDD minus R times beta F times I base, right? Because that is the current in forward active through R, where Q2 is in forward active initially, forward active till VC becomes, 0.2 volt or 0 volt. Or maybe I should write it formally, becomes V collector emitter SAT voltage, which is 0.2 or 0 volt. So this way, during that time until here, the voltage here, which becomes like VDD divided by 3, the R, no, R actually goes to low right away. It remains here a very short while, and then it goes back, and then, it's going to be like this. And meanwhile, the output switches back to VDD and then remains in there. And then S will remain in here anyway. Okay, so this will be remaining in here until the next trigger comes. I Hope this is clear. And the idea is, again, like, you know, if we do it here until the trigger comes in here, the output will remain like that. And then threshold voltage is initially 0. And then set is initially 0. Reset is initially 0. And output initially VDD. Okay. So and the critical thing, I mean, this will go up maybe like here. No. Okay, the critical thing here is this will go up. So S will follow V trigger, and then R will remain 0, and then output will go down and then remain here. So the critical thing, and then the timing period that we want to calculate is this time. So the goal here is to go to VDD, but you know, whenever this reaches to 2 VDD divided by 3 is the critical point. And so that critical point determines the time period where this will go low and then remain low. And then after that, output goes back to VDD. So this time period is what we really want to find out. And it is equal to this time period, of course. And then, I mean, here for this cycle, we know that the capacitor is charging with a time constant of tau, which is equal to R times C. Okay. So, of course, it will not be reaching to that value. So maybe I should do it like this. You know, the goal is to reach to here, but it will not happen. And so we can find the time period there. How can we find that time period? The thing here is that the time, you know, here between t is at you know, between t is between 0 and t time. In that time period, we know that Vc of t is going to be equal to V final plus V initial of the capacitor voltage minus V final e to the power minus t divided by tau, right? So that is the projection, and initial is 0 volts. So this is 0 volt. This one is VDD, and this one is VDD. And when the time becomes t becomes t, then Vc of t becomes 2 VDD divided by 3. And at that time, the equation is going to be minus VDD e to the power minus t divided by tau. So the only unknown here is t. Okay, so this t can be extracted. Okay, so the t is the unknown value, and all the others are known. So if you you know, do this math here, I mean, you can see that the equation is T, or maybe I should do it like red. T is equal to tau times ln 3, or T is equal to R times C times ln 3. Okay, so this fixed time is determined with our capacitor and resistor values, and ln3 is also a fixed number, right? So by changing and playing with this R and C, you know how long period this trigger is going to be affecting. So this, notice that this T trigger is short, but due to RS memory of the RS flip-flop here, it only changes, and it's enough to change the signal for a short while, but then it will, you know, store its value, and you know, and the R goes for a very short you know, period of time, and that's enough to set this output to back to here. And if you are really interested in, you can also find the value of this charging. Okay, so it's almost not almost linear, but you know, you can also find this maybe another period here. Okay, the X value. So you can find that. How do you find that? We see final capacitor final is equal to VDD minus R times beta F times I base, and then VC initial is equal to 4 volts, or 2 VDD divided by 3. Okay, so the time constant here, tau. So you can also find, you know, X. X can be determined if you want. And why do we care about that X? Because after that time, you know, we can have another trigger. So if you want, you know, one more time, you have the trigger here, and then everything will start again, like, you know, with this next trigger, this will go down. So let me do it maybe a little bit later on. So somewhere around here, we can give another trigger, and then the things will be again like happening here. This will go again down, and then a period of T again. Okay, so I hope this monostable operation is also clear, and please let me know if it is clear. Then if not, I'll try to explain it again. If yes, then we'll stop here and give a break, and then continue with new subjects. Okay, so I'm giving a break here, and we'll do maybe continue, not full hour, but a little bit maybe less than full hour. But I want to start a new subject, memory.